So in our last couple videos about general plane motion, we started talking about how we can approach it with a relative velocity approach. And we actually have two methods that we can use when we're talking about this relative velocity approach. And in this video, we're going to talk about this other method that's called instantaneous center of zero velocity. So in that last video, we were talking about how if we have something that's rolling without slipping, we have this location on that rolling where at the ground, where that point meets the ground, we say at that moment, instantaneously, there is zero velocity at this point on the ground. And when we used that point in our rolling without slipping, it made our calculations just a little bit easier. So what we're going to do is we're going to take that concept of selecting some point that is the instantaneous center of zero velocity and using that as the base point. So instead of our relative velocity analysis where we were taking A as our base point, when we have some rigid body here that is translating and rotating, we were taking A as the base point and basing everything of our relative motion around that base point A. Instead, what we're going to do is we're going to find that point where we have zero velocity. So there is a point of the system that has zero velocity, and if we can find what that point is, we can use that as our base point and simplify the calculations a little bit. Because normally we're working with our VB equals VA plus VB with respect to A, or sometimes we wrote this as plus omega cross product with RB with respect to A, whichever way you want to write that last velocity term. But this equation gets really simplified if instead of using that base point A, we use some point that has zero velocity. And so we call this the instantaneous center of zero velocity. This is the point that we're using. And sometimes you'll see that point shortened to be called IC. So somewhere in the system, there is a point of zero velocity, and we've just got to find it. So that way we can use this simpler form of this equation. VB equals omega cross product with RB with respect to the instantaneous center of zero velocity. And since our VB has to be perpendicular, it has to be perpendicular to our position vector, RB with respect to IC. This we can really just use in scalar form. Velocity of B is going to be omega, our angular velocity, times the distance here, that position vector, RB with respect to IC. So I know it sounds a little bit nebulous, so we'll kind of talk about how we find these instantaneous centers of zero velocity, and then we'll do some examples so that we can see how we can get this simplified form of our equation to work out in our problems. Because usually the harder part in this is going to be finding that instantaneous center of zero velocity so that you can use this easier equation. All right, so it's a little bit of a trade-off. In our last videos, we talked about relative motion with velocity. In this one, we're going to talk about instantaneous center of zero velocity. But in both cases, whether you use that method or this method, you're finding velocities, right? You're going to find the angular velocity, or you're finding a velocity of A or velocity of B or some other, velocity of a point in that rigid body. This is just giving you another method to use for solving problems. Right, so you don't have to use this method. You don't have to use the relative velocity method that we had talked about in the last few videos, but you'll have to use one of them, right? So it's just another tool set. It's the same concepts that we had done in the last one, just a little bit of a different approach in this one. So with that, let's talk about how we find these instantaneous centers of zero velocity. So how do we find these instantaneous centers of zero velocity? Well, there's a few different scenarios that we may encounter, and they each have a general way to kind of find that instantaneous center of zero velocity. We'll kind of look at a general body and talk about how we find that point, that instantaneous center of zero velocity. So what that's going to look like is if you're given a velocity and an angular velocity. So let's say here is our rigid body, here is point A, and let's say it has a velocity that goes like this. There's VA. And this body is rotating with some angular velocity omega. So to find that IC, that where that IC, that I'm going to say IC a lot, but I mean instantaneous center of zero velocity, because good lord, if I have to say instantaneous center of zero velocity, we're going to be here all day. So I'm going to call it IC a lot. So to find that IC point, what we're going to do is it's going to always be perpendicular to that velocity. So if we've got a velocity here, our point that we're interested in is going to be perpendicular to this velocity. So this is kind of a perpendicular line that we're going to use to find it. And then based on the direction of omega, that's going to tell you whether we are kind of in this above area or whether we're in that below area for that vector. And the way we can do this is kind of a throwback to stuff we've talked about in physics and statics and things like that, which is our right-hand rule. Because if we remember, this is a cross product, so we can use right-hand rule anytime we're using a cross product, where your index finger, what we're going to do is we're going to use this like 3-finger method, where your index finger goes in the direction of your position vector, and then your middle finger gets pointed. If I can show you on a better backdrop here. Here's kind of a black backdrop to look at. So your pointer finger, my pointer finger here, is going to point in the direction of R. So like it's either going to be in the up or the down. We're not sure on this one. And the middle finger points in the direction of velocity. That's our velocity. And then my thumb is going to point upwards or downward, right? That's going to be my K value. That's going to represent the angular velocity. Our angular velocity, if we remember, has that K value, where if I'm going counterclockwise, I have a thumb that's like pointing upwards out of the page. And if I'm going clockwise, like we have in this image here, I'm going into the page. So I know I'm going clockwise into the page, and then my middle finger is going to point in the direction, goodness, I can't even rotate my hand this way. My middle finger is going to point in the direction of my velocity VA. So what I'm going to have here is for my instantaneous center of zero velocity, it's actually going to be beneath. So to get this correct rotation, I can draw this. R of, and it comes out to this point where this distance to that IC point is given by our vector R, A with respect to IC is our vector here. Let's see, so I have my finger in the direction of my R vector, and then my middle finger, so nope, I actually drew this backwards. My mistake. So see, I right-hand rule, I caught myself. I didn't have my hand correct before, so it's actually not down there. Let me try up here. So if I point my finger downwards, and then my middle finger in the direction of VA, then I get that my thumb points into the page, points away from me, so that's the correct direction here. So my IC is some point out there, where this position vector, R of A with respect to IC, can be found with R of A with respect to IC equals omega times, no, not times, sorry, I have this written backwards. our position of r, a with respect to IC, is the velocity of a over omega. Because those are both given, right? We were given VA and omega. That's what we started with. So if both of those are known, we can calculate what that distance is. So that direction is given from our right-hand rule and from it being perfectly perpendicular here to VA. And then that distance, the overall distance, is given by this equation here. Okay, we have that relationship where VA equals omega times RA with respect to C. So rearranging it gives us RA with respect to C equals VA over omega. Oh, okay. I know it was a lot, and these make a lot more sense with examples. It's really hard to kind of picture these centers of instantaneous velocity, but imagine that this is like the center point that this thing is kind of rotating about. This is where the system itself has no velocity. Right? So it's not necessarily like the point that the bar is rotating about, like as, you know, the bar is rotating and translating. It just happens to be that at that point in time, there is no velocity here in the system at this point IC. Right? Just like when we had that rolling object and we had this moment where we had no velocity when it is touching the ground, we have that for any given system. So that's what we're doing here. We're trying to find these instantaneous centers of zero velocity in these different scenarios. So this is one that you'll commonly come across, is you're given a VA and an omega, and this is how you find the IC and that relationship between them. Another one you'll commonly, very, very commonly see is that you're given two velocities. Right? So maybe you're given VA and VB, where you have, let's say, I've got some body. Could be any shape. I tend to just use like a rectangle because that it's easy to draw. Even that I don't draw very well, but I'm doing my best. And you're given some, let's say you've got VB here, and I'm just going to do VA as something that is in line with the bar here. So you're given a VA and a VB. If you're given a VA and a VB, to find that instantaneous center of zero velocity, you're going to take the perpendicular lines from each of these. So perpendicular lines straight out from both VA and VB. And this one's a little bit easier because you don't have to mess with which side these things are coming out of, because they're only going to cross at one location. So here when I bring out those perpendicular lines, perpendicular from VB, perpendicular from VA, I get this point here. And this point where they intersect, that's my instantaneous center of zero velocity. And from there, I can write out these position vectors. So here I've got position vector from B, or B relative to instantaneous center of zero velocity, and RA with respect to IC. So I can find both of those vectors, typically with trig, right? So sometimes you can use your your angular velocity isn't given to you here. You might be able to calculate it, but typically these values and their relationships are found with trig. I'm just going to say under here, use trig. And when I say that, I mean like your basic sine, cosine, tangent, but I also mean sometimes those special things like law of sines, law of cosines. Those may come in handy as we're figuring out these problems. But this is a very common one. So use trig, so that's your, sine, cosine, tangent. Law of sines, just as a quick reminder, is your sine of A over side A equals sine of angle B over side B equals sine of angle C over side B, or side C. So any of those, we typically use trig relationships to find those R values. with respect to that IC. And then the last one you may be given is kind of a special case, and you often see it with circles or things that are kind of rolling and translating. Circles tends to be where I see this the most, where you're given VA and VB, but they're parallel to each other, right? So if you have, I'll just do it, I'll do it as a circle, I suppose, where you have maybe a VB on the bottom, so that your instantaneous center of zero velocity isn't at the bottom there. Maybe it's on some kind of conveyor belt. The bottom is moving for some reason. The ground isn't solid. And then this is VA. So your VA and your VB are different. They're different magnitudes from each other. And the way that you find that instantaneous center of zero velocity is that you create this kind of ratio of triangles between VB and VA to find this IC location. And the way that you can relate these is again with RA with respect to IC is VA over omega, and RB with respect to IC is VB over omega. And even though we're not given our omegas here, what we often do is we equate the omegas in each of these equations, where we get some relationship that says VA over RA with respect to IC equals VB RB with respect to IC. And so we have this relationship between the two of them, and we can use things like our radius here, and let's say like a distance x that we can solve for to relate these two together. Right, and then we can solve for some of our unknowns. We can solve if we don't know the angular velocity. But this is typically how this is found. It may also be if VA and VB are in the same direction. So maybe you have this same scenario, but instead you've got VA and VB. Again, that IC is still perpendicular. It's still perpendicular, and it's still kind of related as this ratio of that VA and VB, but your IC is going to be up outside of that circular object. I know it feels a little arbitrary. It probably doesn't make a ton of sense just yet, but we're going to look at some examples of how we find these instantaneous centers of zero velocity, and then we're going to also do some problems working through them. And I think the more you do some problems and do some practice with it, you'll see that it kind of makes sense as an approach, especially in some problems over others. But again, it's just another method for you to use, just another tool in your tool belt here. All right, so before we get to some real examples, let's kind of take a look at these more like conceptual examples of how we find this instantaneous center of zero velocity. So I've got a few examples written out here on the left, and we'll kind of talk about each one and how their approaches may differ a little bit between them, and how we can kind of think about these in dynamics in the way that they are moving. So this first one, we want to find where that instantaneous center of zero velocity is for our member BC. And although it might not be like intuitive just looking at this, you're like, Professor, all I see is an angular velocity about A. what do I do with that? Well, you think about the motion of the problem, the motion of this piston, what's happening with BC. So like if we look at C, for example, we know C has to be moving either left or right? It's constrained there in that little fixed groove. So it's moving either left or right. And then looking at that angular velocity that's over there by A, we can kind of see, because that's moving about the fixed point A, it's rotating clockwise in this case, that our C has to be moving to the right. Right? When that AB is swinging down in that clockwise manner, it's going to force C to move to the right. So we do know the direction of VC, right? And we don't actually need to know the magnitudes when we're finding our, like the general location of our IC. We can do it just with our directions here. So I know the general direction of my VC. It's going to be to the right. And then I think about my point B over here. And if we remember, when we have something that's rotating about a fixed axis, as we do here for member AB, our velocity is just perpendicular to that motion, right? So B is swinging down through this due to this angular velocity omega. So it's just going to be perpendicular to that bar AB. Right, this is back a few videos ago when we were doing rotation about a fixed axis. It's going to be just perpendicular here to bar AB. That's the direction of our velocity of B. And now I'm not actually sure if I have enough room to draw this. I guess we're going to find out. Where we're going to take our instantaneous center of zero velocity for a case like this, where we have the directions of our VB and VC. We're going to draw out perpendicular lines from those velocities to see where they intersect to find IC. I'm going to draw my perpendicular line straight out from AB there. And then my perpendicular line straight up. That's not straight. Let's try again. So, my little trackpad isn't always the easiest to write on. Then like that's vertical though. And we find this point where they intersect. That's the location of our instantaneous center of zero velocity. And like we said, it's usually a little bit easier to relate these guys with trigonometry. So they make a little triangle where BC is usually of some known length. And you can typically find some of these angles in here. So you can find that RC with respect to IC, BC with respect to IC, and any of the values that you may need in relationship to that. So you can find velocities or the distances or angular velocity, any of those that we may need in these relationships. So that's how we would do it for a basic member where we can kind of figure out what those velocities are. So then we'll take a look at this next guy. We've got this disk that's rotating on a moving conveyor belt, right? So my disk is rotating actually in a counterclockwise way, but we'll notice it's on this belt that's moving with some velocity v. Right, so we've got kind of these different directions going on here where we can't just say, oh, my point A has zero velocity because it's on that conveyor belt. So I've got to kind of think about how this thing is moving all together. So with this, I'll draw my circle again over here. I know that that point A is moving with velocity v. And they gave us that that was 8 feet per second. If we felt like, you know, actually calculating this out and finding what the value is. This velocity is 8 feet per second. And they gave us an omega of 2 radians per second. They didn't tell us what our center velocity is, but because this conveyor belt is moving us along, even though we're rotating in the other direction, the overall shape, the overall cylinder as it's rotating is going to be moving to the right. And I'm going to call this VC. So that's kind of like my parallel line, right? I've got these 2 parallel velocities going on. So my instantaneous center of zero velocity is going to be somewhere up here that makes a triangle with like the relationships of BC, or the center of that guy, and V. It makes kind of a triangular ratio relationship. It's not the best looking. I think I drew it a little bit too high. Something like that, maybe. And we can actually find the value of this length. We know it's perpendicular to those v's because we know that all of the velocity is pretty much heading just in the to the right. And we had this relationship, right? We said r of a with respect to IC is going to be v a over omega. And so just doing that exercise kind of in this little mini problem here, VA, at point A at the bottom was 8, and then that omega is 2. So this distance here from IC to point A, so R of A with respect to IC, is going to be 4. So this distance here is 4, and we know it's straight up and down because it's perpendicular to V. And we also know that this radius is 1 foot, so we've got 1, 2, so mine's a little short, 3, 4, coming up above there. And then this connection, we could use the ratio triangle relationships to find VC if we wanted to. Right, so this is just kind of a mini example of one where we have a disk rotating and the IC is outside of that disk. But what if I take a look at this next one? What if we look at this next disk where we've got a velocity? Let me kind of draw this guy a little bigger too so he's easier to see. Where point B at the bottom here has a velocity of 2v, but point A at the top has a velocity of just v. Right, so what we've got going on here is we've got two velocities, both parallel to each other, where we know that this IC value is going to fall somewhere in between them, right? Perfectly perpendicular, somewhere where we have the middle of our guy. Our IC is going to fall somewhere in the middle there, where it's going to be proportional to the relationship between this V and this 2V. Okay, so there's IC, and we would have our vector of RA with respect to IC, and RB with respect to IC. Right, so it's going to be somewhere in the middle there, in the middle of that disk, not at the center point, right, not at the centroid of the disk, but at the instantaneous center of zero velocity. So different than just the center. It ends up being a relationship between our angular velocity that we develop with those velocities and our r's to kind of figure that out. So let me kind of show you, if you wanted to find like the actual value of where this IC is, kind of how we would approach that. So let's say that my distance from B to the IC is x. And I know the overall height of this thing is 2 times r, right? Just leaving it in generic terms. So we said that r of A with respect to IC is going to be V over omega, right? And that V, that's that top V up there. And then we have R of B with respect to IC is going to be 2V. Our velocity is 2V on the bottom there, and then omega is the same for both. We weren't given an omega, but we know that omega is going to be the same for both of those points as it's rotating around. But we can also relate our RA with respect to IC in relationship to the distances, in relationship to our radius, because we know it's straight up and down. It's just straight through the middle of our disk here that's spinning. So I also know that this distance here of my A with respect to IC, this little distance, is going to be 2r minus x. And I can do the same with AB. This distance we already labeled as x. So I can set those each equal to x. And then I don't need to worry about these RA with respect to IC, RB with respect to IC. I can just use these relationships that I have over here now, right? These equations that I've got here to solve for this x value, to figure out where exactly IC is hitting. So since I don't know omega, I think it's going to be a little bit easier for me to kind of rearrange so that I can solve for an omega and do a substitution. So what I mean by that is I'm going to take the second equation here. I'm going to rewrite it as 2v over x equals omega, and then plug it into the top equation relationship so that I get v over, oh gosh, it's going to be kind of a gross fraction, 2v over x equals 2r minus x. So if I kind of rearrange this a little bit, my v's cancel out here, my x comes to the top, so I get x over 2 equals 2r minus x. If I add that x over, I get 3x over 2 equals 2r. And then dividing that over, I get, I'm going to move over that 2/3. So I get that my x value is going to be 4/3 r. So whatever that radius is, it is 4/3 of r. So it's just above my center there at 4/3 r. And so it kind of makes sense. It's still within that disk. It's not, you know, way out in no man's land, kind of like our problem, our disk before it was. But it's somewhere in the middle there, and we can actually find that relationship, find where that IC is, and then we can go back and relate this to the angular velocity, for instance, if there's something else that we need to find. And then we've got one last guy at the bottom here that we want to find where that instantaneous center of zero velocity is for AB. So AB is really our only member there. And we can see that we've got an angular velocity of this disk. So what's really interesting about this disk is that it's on the ground. So like the disk itself has an instantaneous center of zero velocity. It's right there, right? That point on the ground is the IC for the disk, right? For the way that the disk is moving. So if we remember, we can come from this IC of the disk to point A to find where velocity A is pointing. So the velocity of A is perpendicular to that. Velocity of A is perpendicular to that. And then kind of thinking about the motion of how this would be happening is when we have that angular velocity there rotating kind of over, going to the left, it's actually pulling B to the left as well. B is sliding on the ground directly to the left, BB. So again, this is actually going to work just like the first one. We have two velocities again, VA and VB, and we're just going to find where those perpendicular radii intersect, where those perpendicular position vectors intersect. So I'm going to come out perpendicular from VA. It passes through that same instantaneous center of zero velocity of the disk itself, but comes all the way, and I've seemed to have run out of room here. Give myself a little more. There we go. So going through that instantaneous center of zero velocity of the disk until we meet up with this perpendicular position from VB. So it's where those positions of VA and VB, those perpendicular position vectors, intersect. That gives you IC. So then you can find your B with respect to IC, your RA with respect to IC. And again, typically by trig is how you do these relationships. You can find these angles, you may have lengths that you can use to find the trig relationship between these and solve for any values that you're missing. And again, I know it's not an easy concept to grasp. It's difficult, and it takes some getting used to and some practice. And hopefully it'll make a little more sense as we get into some examples, so you can actually see how we use this center. Let's take a look at this first example, where we've got bar AB that has an angular velocity of 4 radians per second, and we want to determine the velocity of slider block C at the instant shown using the IC method. Alright, so looking at what we've got here, I'm going to kind of break up these two bars that we have into two different diagrams so we can kind of look at what's going on here. So AB, have here's our AB. We're given an angular velocity for AB of 4 radians per second. And we'll notice that this is actually a rotation about a fixed axis. Right, so we can go back to a couple videos ago when we were doing just rotation about a fixed axis, and thankfully that had a pretty simple equation where we said VB for this guy is just going to be omega AB times R of B with respect to A. Right, so that's our omega times our distance, and that VB is going to be perpendicular to R of B with respect to A, right? Perpendicular to that member there. So we can actually go ahead and calculate this. Like, we can work with the math that we have. We know that our omega is 4 and that our distance there is 150. So VB is going to be 600 millimeters, since I didn't convert, millimeters per second. And so that's really nice, because what we can do is we've got that member CB here, where VB is going to be the exact same. VB is still in this exact same direction, exact same magnitude. And then we can also think about, well, how is block C moving? Right, this is what we're trying to find. We're trying to find the velocity of our block C. We know it's either going to be left or right. It's stuck in that little fixed track, so C can only move to the left or right. And the way that B is pulling it, I'm going to go ahead and assume that our velocity of C is pulling that block to the right. So this is great, because with this, not only do I know what VB is, but I know the directions of VC and VB, so I can use my instantaneous center of zero velocity by creating those perpendicular lines to see where that IC value is. So we're going to bring our perpendicular lines, kind of come straight down. Right, perpendicular to VC is going to be this vertical line, and then perpendicular to VB is going to be this line that is at a 60-degree angle, and where they intersect here is IC. Right, so what I've got, I kind of write out my big relationships. I have R of B with respect to IC. I've got R of C with respect to IC. I have my VC. I have VB. I know this length here of member CB that was given as 200 millimeters. And so what I'm going to do is I'm going to create a triangle relationship with these guys. Because what I'm trying to do is I'm really trying to find what that VC is. And that VC relationship, I know the equation that I'm going to use. This is the equation that we had talked about at the very beginning. It's just omega of BC times RC, R of C with respect to IC. So I need both of these things, right? I need some way to find both of these things. And I can clearly see that if I make a triangle here, I can get that R of C with respect to IC. And then I also know that I can use that to find my omega, because I have this relationship of VB equals omega BC times RB with respect to IC. And I know what VB is. So if I can find this guy, I can find my omega BC. I can use that to plug it in up here. I can find my R of C with respect to IC and find my velocity of C. Which I know it sounded like just a lot of letters. But essentially, these are my two base equations, right? These are the two base equations that we're working with when we're doing these IC problems. So we're setting up finding our IC so that we can use these equations essentially just to find the velocity of C. That's all we're looking for. We're trying to find that velocity of C. Okay, so I'm going to take this triangle that I made, and I'm going to make him a little bit bigger so that I can kind of see a little better what I'm working with here. So I've got, maybe I'll just draw him down here. Here's the triangle I'm working with. I need to find RC with respect to IC, RB with respect to IC. I know this length here, right? This length is given. It's 200 millimeters. It's just the full CB. And now I also know some angles in this triangular relationship, right? So if I I'm really going to run out of room on this diagram, but I'm going to try to draw in some of these angles for you to see on here. If this is our horizon here, this line that is perpendicular to VB is actually exactly the same line as AB. So we know this angle that R of B with respect to IC is making with the horizontal is 60 degrees. Okay, so if I kind of put that in down here, this is 60 degrees because this is 60 degrees, right? They're the exact same angle. So if that's 60 degrees and this RC with respect to IC is a vertical line, then that means this interior angle has to be 30 degrees. 90 minus 60 is 30. So that's one angle that I have in there. And then I can also figure out my other angles, looking at my original drawing over here, kind of referencing that and seeing what angles I'm given for things. So because this angle is 60, that also means when I come through this point here at B, that this partial angle down here, let me clarify that one a little bit. This partial angle here is also 60 degrees. Right, that's our complementary angle. I know that this portion is 60 degrees, and I know if I come upwards, we had this angle of 30 degrees between the y-axis and CB. So this angle is 30 degrees, which means that this other side of the interior angle must be 60 degrees, right? Because they make a right triangle there. So I know that this is 120, which means this last angle has to be 30. So now that we were able to deduce all of those interior angles of this triangle, I can use some of these relationships to find what RC with respect to IC and what RB with respect to IC are. So my, and I think honestly the easiest way to do this is probably going to be law of sines. Right, if I do sine of 30, I'm taking this angle here, and then matching it with the across, sine of 30 over, whoops, that's not right, sine of 30 over 200 equals sine of another angle, so let's take this one, sine of 120, and the one across from it, RC with respect to IC, using law of sines, I can just solve for what that value is, what that RC with respect to IC is. And I get RC with respect to IC from a calculator. I can get that as 346.4 millimeters. Right, and I can do the same thing to find RB with respect to IC. And that one is even easier because it's another 30-degree angle. So my sine 30 over 200 equals sine 30 over what? 200. That one's a pretty straightforward law of sines. Or really just law of symmetry, just by symmetry. It's an isosceles triangle. We can figure out that RB with respect to IC is 200 millimeters. All right, so we got some of that geometry stuff out of the way. That gave us some of the components for these guys. It gave us our numbers that we need for these guys. And we know what VB is, right? We found it over here. So I can actually go ahead and solve for that omega. So omega BC equals VB over RB with respect to IC. My VB was 600 millimeters per second. And that R that we just found was 200 millimeters. So when I divide those, I get my omega BC is 3 radians per second. 3 radians per second. So now that I have that guy, I can plug it in here and find what VC is. So VC equals omega BC times RC with respect to IC. Scroll down a little bit so I can see those numbers. VC is 3 radians per second times 346.4 millimeters gives me 1039 millimeters per second. 1039 millimeters per second. So even though like the IC portion can feel a little bit convoluted and you're like, why am I having to do all of this trig? Why would I do it this way? Really, it's just another method to do it. Instead of doing it with your scalar analysis or vector analysis as we did in relative motion, you now have this way to do it with just trig and not having to worry so much about your signs, not having to worry so much about, did I get the correct vectors? You're kind of just building out this triangle, these relationships with your IC to kind of simplify some of the math of it all, right? You're using simpler equations, but you're doing a lot more trig to get there. You're doing a lot more just your basic geometry kind of stuff in order to find your answer. And actually, you may have noticed that we've done this problem before. We actually did this a couple videos ago in our relative velocity lesson. So this was an example problem in that lesson. And so I wanted us to work it again here so that you could kind of compare and contrast and really see the difference in that methodology versus this methodology. Again, not that one is better than the other. You can really use them for the same use cases. There just may be times where it's a little bit easier to use one over the other. Or maybe you have a personal preference and you want to use one over the other. Both of those options are there for you. Let's take a look at another example. So here we've got block D that moves with a speed of 3 meters per second. Determine the angular velocities of lengths BD and AB at the instant shown. All right, so 2 angular velocities, so 2 omegas that we're looking for. And let's kind of break this shape out into some kinematic diagrams kind of based on our pins, based on what we're seeing. So first I'm going to notice, kind of just working from left to right, I have another pin member A that is a fixed rotation. All right, so I immediately am going to know, since I have that pin member A, my velocity of B here VB is going to be perpendicular to that member AB. And this is also going to kind of help me note direction, right? So I know that around point A, my omega AB has to be swinging in this clockwise direction. But I don't really have any like usable information for this section AB, right? For this little portion AB. All it really did was kind of give me a direction for VB. So what I'm going to do is I'm going to go ahead and work on my other diagram, this other leg here of BD. So, and let me label these. So this is AB and this is BD. And actually I'm going to move that out a little bit. So I have enough room here to write. And I'm going to go ahead and put all my velocities that I know on this, because I do know my VD. That was given, right? This is our VD is 3 meters per second. And we know it's moving to the right. And then we also have the direction there of VB. So the direction there of VB, and I know that these don't like look the same necessarily in the way that I've drawn them, but it shows here that our BD and our AB, these two members, are perpendicular to each other. So this VB really is like right on this member. It's right in line with that member. Even though they don't look like they're facing the same direction in the way I've drawn them, that's because I'm not the best at drawing. So that's my mistake. Maybe I could curve it just a little bit more. I do that without it looking terrible. Well, it doesn't look great. It doesn't look amazing. Maybe like 10% better. It's not great. We'll leave. You know what I mean. Yeah, we'll leave it like that. The point is that we're finding our IC, right? We're finding our IC relationship so that we can find these angular velocities, because we know that we have those relationships where we can say, you know, BD equals omega BD times RD with respect to IC. Or we could do it with B, depending on kind of what approach is going to work for us. So VB equals omega BD times R of B with respect to IC. And then, whoop, that's B, that's a BD, that's a D. Alright, I'm getting sleepy and now I can't write anymore. Goodness. And then of course, because this guy's a fixed rotation over here, we know that VB could also be related with omega AB times R B with respect to A. Right, so that is really kind of the only thing we're given over here. We know that this is 0.4 for this R of B with respect to A. But we don't know what VB is, and we're trying to find these angular velocities. Right, trying to find those angular velocities is our goal for this question. So knowing that that's what's in our mind, we need those R relationships, we need those position vectors, so we're going to find IC. Right, and again, it's perpendicular to our velocities. So coming out perpendicular to VB and coming out perpendicular to VD. Straight up, my IC is going to be somewhere up here, where this leg of my triangle is R of D with respect to IC, and this leg is RB with respect to IC. And if I start kind of putting together my angles in that, notice that since I said we have this 90-degree angle here as indicated in our drawing over here, that means we're also going to have a 90-degree angle here. And if I look at this relationship of angles over by D, when I draw a straight line out for this 45 that we can see, whoops, that we can see over here, that means that this angle is also going to be 45 degrees. Right, so I've got this really nice right triangle relationship where I can find RB with respect to IC and RD with respect to IC with just my standard trig relationships, right? My sine, cosine, tangent, those things. So for my, and then of course I have that length. That length again is 0.4 meters. If I kind of draw this as like a cleaner triangle, I have a right angle here. I've got my 45 degrees. RD with respect to IC, RB with respect to IC, and 0.4. So I want to find those lengths so I can come plug them into my equations that I've created. So if I want to find my R of B with respect to IC, I can relate that to the 0.4 here with a tangent of my 45. So tan 45 is going to be opposite over adjacent. So opposite is RB IC over adjacent is 0.4. If I rearrange, I get my RB with respect to IC is just 0.4 when I plug that in the calculator, because tangent of 45 is 1. The tangent of 45 is just 1. My RB with respect to IC, I can do the same kind of process with my RD with respect to IC. And since that is the hypotenuse and I know my adjacent, I can relate those with cosine. Cosine 45 of adjacent 0.4 over hypotenuse RD with respect to IC. I can rearrange and pop it in my calculator. RD with respect to IC is 0.567 meters. 0.567 meters. Which is great, right? Because now that means that I have these guys of my equations. And what else do I have? I have VD, right? They gave me VD. So since I have VD, I can go ahead and solve for omega BD. So omega BD, again, coming from this equation here, omega BD is going to be VD over R of D with respect to IC. VD, we said, is 3 meters per second, and that R value we just found was 0.567 meters, and that's going to give me an omega BD of 5.3 radians per second. 5.3 radians per second. And now that I have that, the other thing I'm looking for is angular velocity of AB. So angular velocity of AB, I know I've got this relationship up here where if I can find VB, I can plug it into this relationship to find omega AB. And thankfully, now with this guy, I can plug him in here. So VB equals 5.3 times my RB with respect to IC, so times 0.4. So VB is going to be 1.12 meters per second. So very last step is that this guy is coming up here. And we're going to solve for omega AB. Omega AB is going to be VB over RB with respect to A. So VB is 1.12. RB with respect to A, that's just the length of this rod, so that is 0.4 meters. So omega AB is also, coincidentally, 5.3 radians per second. And it's kind of coincidental, it's kind of not, since these two members are the exact same length, like AB and AD, or yeah, AB and BD are the exact same length, and they meet at a 90-degree angle. So, like, yeah, all of their math is going to be equal, right? They're gonna go through the exact same angular velocity there because of the angle that they're at right now. All right, let's do one last example, and this one will be just a little bit different from the last ones that we've seen, in that instead of doing that methodology where we're doing the perpendicular, we've got two velocities that are kind of pointed in different directions. Now we've got two parallel velocities that are given to us. So here we have a cylinder shown rolls without slipping between the two moving plates E and D. Determine the angular velocity of the cylinder and the velocity of its center C. So let me kind of zoom in. Let's draw, whoops, sorry, microphone. I'm sorry, everybody's ears if that was loud. So we're gonna kind of zoom in on this cylinder, take a look at what's going on and how we're gonna look at this instantaneous center of zero velocity and how we can use that to kind of figure out the angular velocity and our velocity of our center here. So I'm going to draw like a bigger version of that circle, and we can see that we have VE, okay, so point E, or I guess point A at the top here, that velocity of E, so plate E is moving at 0.25 meters per second, which is causing point A to move at 0.25 meters per second. And so I'm going to call this VA. And then we have the bottom here, B. Since the ground is moving, it's not 0 at B, but instead is how D is moving. So that's, whoops, that's a little bit not straight. That's, I don't know, that's like 10% better. BD is 0.4 meters per second. So we know that the IC is going to fall somewhere on this line between them, right? That straight line between them. And here is our regular center at point C. And actually I'm going to call this bottom velocity, I'm going to call it VB just for consistency's sake, because B is this point on the bottom, and then A is this point up here. So our instantaneous center of zero velocity for a disk like this, when you've got those two velocities that are going in different directions, you're going to have essentially like, you're relating the magnitudes essentially to figure out where that IC is. So here I've kind of drawn them, almost proportionally, I would say, where you can see the velocity arrow I've drawn up top is a lot shorter than the velocity arrow I've drawn at the bottom. But really what I kind of want you to think about is that whatever number is lower, that's the one where IC is going to be closer to. So like since VA is a lower number than VB, our IC is going to be closer up here. It's going to be closer to VA than it is to VB, just because it's a lower number. Okay, so somewhere in here, we're going to have that center of zero velocity. And in order to find that, label that IC, where we have these vectors that can represent, so RA with respect to IC, and then here we have RB with respect to IC, and we know the radius of this. So the radius is 0.125 meters. All right, so I think I've captured everything that we can. And what we're going to do is we're going to find this IC so that we can create those relationships where our VD equals omega times R D. Why do I keep writing D? I mean to write B. VB equals omega, because we've got this guy is rotating through some angular velocity omega. All right, so VB equals omega times R B with respect to IC, or we could use VA equals omega RA with respect to IC. Right, and we're trying to find that omega value. We're trying to find that angular velocity. So what I'm going to do is I'm going to say, all right, this distance here from B to the IC, I'm going to call that X. And then I'm going to plug it into each of these equations here. So I know what VB is, and I don't know what my R values are, but I can relate my R values with my overall radius and with my X. So for example, R of B with respect to IC, I can see that that total distance is going to be X, as I've called it X here. And RA with respect to IC, I can see that that is the overall diameter of this cylinder minus X. This distance here is going to be our overall diameter minus X. So the overall diameter, we're given that radius of 0.125, that means my diameter is double that, 0.25 minus X. So I'm going to go ahead and plug those into my equations over here and just see how far I can get with them. So VB is 0.4 equals omega times X. And then I have VA is 0.25 equals omega times 0.25 minus X. And notice those are two different values. This 0.25, this one is a velocity. This one is the diameter. Right? Those are two distinctly different values. All right, and so what I'm going to do is I'm actually going to solve for, I guess you could solve it either way. You could either solve for X and then plug it in, or you could just go ahead and solve for omega in this one. So if I rearrange this equation so that I get 0.4 over omega equals X, I can substitute that guy in there. That I get 0.25 equals omega times 0.25 minus 0.4 over omega. And I can multiply it out. 0.25 is 0.25 omega minus 0.4. And then adding that over, get 0.65 equals 0.25 omega. So I divide the 0.25 over, and I get omega equals 2.6 radians per second. All right, so this is one of the cases where it might actually feel a little bit easier to use that instantaneous center of zero velocity. Right? It was really just a lot of algebra setup to find this angular velocity of this rolling cylinder. All right, so we got omega. Last thing for us to find, we need to find the velocity of the center. All right, so we're finding that velocity of C. So to do that, what we can do is we need that vector from, or of C with respect to IC. So C with respect to IC. So if IC is at X, and we know that this distance, this radius is 0.125, then what I'm going to get is this little distance here is X minus 1.25. So R of C with respect to IC is going to be X minus 0.125. Which I guess means I need my X value. So I can take my omega plug it into this relationship here to solve for x. So x equals 0.4 over 2.6. That gives me 0.154 meters. So RC with respect to IC, 0.154 minus 0.125. And what I needed that for is to find VC, because VC is going to be omega times RC with respect to IC. We know omega, that's 2.6. We know this R now, which is 0.0, oh, I didn't write this down, 0.29. Hope that's right. I would do it in a calculator, don't trust me. Check all these numbers in a calculator. You don't know if I'm lying to you. You know, I make math mistakes too, you know. I punch in incorrect things in a calculator all the time. You should always double check what I'm doing. Always double check yourself. This is what's also really great about having this method of instantaneous centers for zero velocity, is you could try it the relative velocity way and you can try a problem this way. And if you get the same answer both times, that's a pretty good sign that you're doing something right. So anyway, as an engineer, you know, it's just always good to check. It's just good to check. Anyway, so we plug that into the calculator and we get 0.075 meters per second. And we know the direction on this actually. It's kind of based on how this line hits. So this direction is actually going to be to the left. It's very small, but it is to the left here for our VC of 0.075 meters per second.